Welcome to this video on the moment area method. This is one of several videos in a short course on the analysis of indeterminate structures posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. The moment area method is a technique for calculating displacements and rotations in beam and frame structures. That is why it appears in this slide under the deformation category. However, in this general slide that appears in many of the videos in this short course, it says truss and frame structures at the top. That does not apply to the moment area method. This method does not work for truss structures, only beams and frames with a known bending moment diagram. That point is expanded on the next slide, which spells out a few features of the moment area method. First, we must have determined the bending moment diagram by some other method. For example, for a statically determinate structure, we must have used equilibrium in order to determine the bending moment diagram. Conversely, for a statically indeterminate structure, we must have used a method such as the flexibility method in order to obtain the bending moment diagram. The next item on this slide makes the point that no further analysis of the structure is needed. That contrasts with the virtual work method for calculating deformations, which requires the analysis of the structure subjected to a unit force or moment at the location where we want the deformation. This is why the virtual work method is awkward for statically indeterminate structures, unless it is used as part of the flexibility method. Unless the flexibility method is used in the build-up to the calculation of a deformation, we need to reanalyze the structure for a unit virtual load, which can be a considerable amount of work for a statically indeterminate structure. This is why the moment area method is ideal for finding deformations in statically indeterminate structures for which we have already obtained the bending moment diagram. There is no need to reanalyze the structure. In order to get into the details of the moment area method, the next slide gives an overview of the equations that appear in Euler-Bernoulli beam theory. This slide is taken from the video on Euler-Bernoulli beam theory in the short course on structural members. As always in terje's toolbox, we have equilibrium on the left-hand side, kinematic compatibility on the right-hand side, and material law at the bottom. In order to formulate the moment area method, we do not need to consider the equilibrium equations that connect the distributed load on the beam with the bending moment. Rather, we combine all the other ingredients of this boundary value problem in order to express the bending moment in terms of the displacement of the beam, denoted by W. The result is that the moment is equal to EI times the second-order derivative of the displacement, circled here in red. We need to pick up one more thing from this slide, and that ingredient appears on the right-hand side. Here, the three equations that together form the kinematic compatibility equation in Euler-Bernoulli beam theory are spelled out. The one we are particularly interested in is circled in red. It says that the rotation at a point along the beam equals the derivative of the displacement. Suppose we differentiate that equation with respect to x. We then find that the derivative of the rotation is the second-order derivative of the displacement. Now, let us substitute that second-order derivative into the other equation circled in red. We have then found that the derivative of the rotation is equal to m over EI. That is exactly the equation written at the top of the next slide. That equation can be solved for d theta, which is the rotation of an infinitesimally short segment of the beam, having length dx. Notice that this rotation is m over EI times dx. That rotation, d theta, is the central quantity in the moment area method. The first theorem of this method states that we can integrate all those small rotations, d theta, along a beam in order to find the change in rotation between the 2 points we integrate between. The integral is written below and demonstrated on this slide for a cantilevered beam with a point load at the tip. The bending moment diagram is shown below, having the value F times L at the base of the cantilever. We have already seen that m over EI, namely the curvature, is a central quantity in the moment area method. That is why we draw a diagram below that is the bending moment diagram divided by EI. This is a curvature diagram, in the sense that it shows the amount of curvature at different locations along the beam. Naturally, there is more curvature on the left-hand side where the bending moment is largest. With that diagram, we are ready to evaluate the integral. Because of the triangular shape, we have a factor 1/2 in order to determine the area of the curvature diagram. The result is the change in rotation between A and B because the rotation at A is known to be 0. Because the beam is completely fixed there, the result of the integration is actually the rotation at B. The first theorem of the moment area method is here showing us that the rotation at the tip of the cantilever is FL²/2EI. On the next slide, we start thinking about finding displacements. This is referred to as the second theorem of the moment area method. Notice that the rotation, d theta, appears to illustrate the change in rotation between 2 points that are the distance dx apart. Next, we draw tangent lines from those 2 points. Those tangent lines are marked with the blue color on this slide. As we go further away from the location we are drawing the tangent lines from, those 2 tangent lines diverge more and more. In fact, when we go a distance, x, away from that location, then the 2 lines are separated by the rotation, d theta, times x. That distance is denoted by dt and is called the tangential deviation. When we substitute the expression for d theta from the previous slide, then we end up with the expression that says the tangential deviation is m/ei times x times dx. So far, this is not giving us any practically useful displacement. It is only when we integrate the tangential deviation, dt, along some portion of the beam that we obtain something that may be useful. This is the reason why the symbol t is defined at the bottom of this slide as the integral of dt between 2 points A and B along a beam. However, it is still not clear exactly what displacement this is. That leads to a major insight into the moment area method, namely that the calculation of displacements is structure specific. We cannot say much general about how to calculate a specific displacement, other than referring to the formula at the bottom of this slide. In other words, the moment area method needs to be taught by addressing specific examples. For that reason, let us consider the simply supported beam on the next slide. It is subjected to uniformly distributed load, and we wish to determine the vertical displacement at the middle of the beam. For this specific case, we recognize that the rotation at that location is 0 because of symmetry. That is why we draw a tangent line from that location. Notice that we must sketch the displaced shape of the structure in order to use the second theorem of the moment area method. That deflected shape is shown with the blue color here. The bending moment diagram, which must be known before we start applying the moment area method, provides help when sketching the displaced shape. Now, observe that the vertical distance from the tangent line to the beam at point B is the displacement we are seeking. We will soon calculate the value, but notice what we just did. We identified the distance between a tangent line and the beam itself at a particular location. This is how we apply the second theorem. In other words, this is how we use the formula that was derived on the previous slide. We identify the distance between a tangent line and the beam itself. That distance is a tangential deviation. In terms of notation, the first subscript of a tangential deviation marks the location where we are calculating the deviation. The second index identifies the location where the tangent line comes from. The value of the tangential deviation is always the value of the integral between those 2 points. Now, let us evaluate the integral. Although it is hard to understand this sentence at first, the integrand can be interpreted as the moment of the curvature diagram about the location where we calculate the tangential deviation, with x being the moment arm. It is via that interpretation that we calculate the tangential deviation as the area of the curvature diagram between midspan and point B multiplied by the distance from B to the centroid of that area. That area is marked with the green color in the curvature diagram shown on this slide. Because the maximum moment is QL²/8, the maximum curvature is QL²/8EI. From a formula sheet, shown on the right-hand side, we know that the area within the parabola contains the factor 2/3. Also, we see in the formula sheet that the distance to the centroid of the area from a specific end contains the factor 3/8. This is why we evaluate the tangential deviation as shown here, with the area written with green, containing the factor 2/3. The moment arm, x, must always be measured from the location where we have identified the tangential deviation. That means we must use the fraction 5/8 instead of 3/8 when we calculate the moment arm that multiplies the green area. Notice that length of the portion of the beam that we are considering is L/2. The result shows that the displacement at the middle of a simply supported beam subjected to uniformly distributed load is 5qL to the power of 4/384 EI. The next slide addresses a statically indeterminate beam with known bending moment diagram. That is the reason why the curvature diagram is shown here, with maximum value QL²/8 EI. In this example, we wish to determine the rotation at B and the maximum displacement of the beam. The rotation is easy. Because the rotation is 0 at A, we find the rotation at B by integrating the curvature diagram between A and B. In order to carry out that integration, we split the curvature diagram into two parts, each with a basic geometric shape that appear on formula sheets. In this case, the bending moment diagram and therefore the curvature diagram can be split into a parabola and a triangle, as shown here. That is why the fraction 2/3 appears in the first term in the calculation of the rotation. That term picks up the contribution from the parabola. The second term has the factor 1/2 because it picks up the contribution from the triangle. Notice that the triangle curves with tension at the top, while the parabola curves with tension at the bottom. That is why the minus sign appears before the triangle term. This means that we locally and temporarily decided that contributions from curvature that curves the beam counterclockwise are positive. When the result comes out positive, it means that the rotation at B is counterclockwise. The value QL³/48 EI appears in beam formulas for the rotation at the end of a fixed roller beam with uniformly distributed load. Finding the maximum displacement is harder. One issue is that we do not know the location of the maximum displacement. However, we know that the rotation is 0 at that location. That is why we start by determining the rotation between point A and a point with distance x0 from A. This integral is an application of the first theorem of the moment area method. On the left-hand side are expressions for the parabola and the triangle. We substitute those expressions into the integral, then set the integral equal to 0, because we want the value of x0 that identifies the location with 0 rotation. By solving this equation, we find that the distance, x0, is roughly 58% of the length of the beam. Next, we draw a tangent line from A. That line follows the line of the undeformed beam. The tangential deviation at the location of maximum displacement is the distance from the tangent line and the beam itself. At the bottom of the slide, we carry out the integral to determine that tangential deviation by again using the expression for the curvature diagrams. We also note that the moment arm is x0 minus x, namely the distance from the location of the tangential deviation to a point identified by the variable x, which is the x-axis that runs from A. We conclude that the maximum displacement of a fixed roller beam with uniformly distributed load is roughly QL to the power 4/185 EI. Thanks for watching this video. Please visit Terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.